Hey everyone, we're going to continue on with section 3 over measurement, and we're going to talk about part 2 today. If you recall, part 1 we talked about scientific notation, but in part 2 we're going to introduce the SI units of measurements. Our key question starts off with, what units do scientists use for their measurements? To answer that question, scientists use a set of measuring units called the SI, or International System of Units. SI is just an abbreviation for the System International of Units. It was actually developed in France in 1791, and it's just a revised version of the metric system. So if you hear us say the SI system or the metric system, generally people are talking about the same thing. One thing to note is that scientists around the world actually use the SI system of measurements so they can readily interpret one another's measurements. Most countries in the world use the SI system or the metric system, except for the United States. We use the imperial system, so we're just a little bit off. So first thing that we kind of have to talk about is base units and derived units. Well, the SI system is built upon 7 metric units known as base units. These build the foundation of all other units that come after. So in SI, the base unit for length, which is defined as a straight line distance between two plots, is actually the meter, which is just one lowercase m by itself. The base unit for mass, which is defined as the quantity of matter that an object or sample has, is the kilogram. This is the only one that's different. A lot of people think it's just the gram, but it's actually a kilogram. So here are our 7 base units that are the foundation and what make up our SI system. So the 4 that you guys will need to know are length, which is the meter, and its symbol is just one lowercase m. Mass is kilogram with a K lowercase g. Temperature is in Kelvin. This is a capital. And then time is second, which is S, or you can say SEC for second. The amount of substance we don't hit until chemistry, and then electric current and luminous intensity, usually these are hit in a physics class, so we don't really see those. However, the first 4 do expect to know those and do expect to see those on your test or quiz. Now, additional SI units called derived units are made by combining base units together. And 2 of the most common derived units are volume and density. So again, derived means comes from the base units. For example, volume is defined as the amount of space taken up by an object, and density is the ratio means division, of the mass to its volume. So mass divided by volume. Okay. Oh, it's right there. Density equals mass divided by volume. I'm also going to stir this because it's very important for you guys to know it. Also, please write in your notes that the density of water equals 1 gram per centimeter cubed, 1 gram per milliliter. Please write that down in your notes. Okay. Other derived units are as such. Area is a derived unit because you're taking length times length. Volume, which is one we did on the last slide, is also a derived unit because we're taking length times width times height. So here we have basically length cubed. Density was also one that we talked about. This is kilograms, so this comes from the SI unit of mass and length. Down here, we do mention energy and pressure in integrated science, and these are both derived units as well. Frequency you probably won't hear of until chemistry, and then electric charge is not talked to until we get to chemistry either. So to derive an SI unit for density, you can actually divide the base unit for mass divided by the derived unit of volume. Because remember, mass divided by volume equals density. So dividing kilograms, which is the SI unit for mass, by cubic meters, which is the SI unit for volume, yields the SI unit for density, which is kilograms divided by meters cubed. Because looky here, you're taking mass, which is kilograms, and you're dividing it by meters cubed, which is volume. A good example of density is a bar of gold actually has more mass for the amount of space that it takes up than a feather does, so gold typically has more or a greater density. The next kind of thing to hit on are metric prefixes. Now, sometimes when we use these base units, we add a prefix in front of them. It's usually sometimes convenient. A metric prefix indicates how many times a unit is multiplied by 10. And we've actually already seen one of these prefixes being used, and that's kilo. If you remember kilogram, kilo is our prefix on our base unit, which is gram. Other common ones that you might remember is centa, if you've heard of centimeter, or milli because of millimeter, or micro because of microorganisms. Please note that their symbol is specific. Here we have an M, and here we have an M. Notice one's capital and one's lowercase. It's important to remember you make that distinction. Capitalization matters. Now, one thing to note about a prefix is it's always used with another symbol. So I'm going to put that over here. Always used with other symbol. So here is where we're going to see our different things. I have this chart on your homework. You guys are going to use it. It's our metric conversion chart. And it's going to help us convert between these different prefixes that we just saw. So here we have kilo. Kilo, remember, is a lowercase k. Hecto, generally we're not going to mess with this. Neither we are going to mess with deca either. Then we get to our base unit. Our base unit are single letters by themselves. And this is going to be something like gram. Here, I'll write down here. G equals gram. L equals liter. M equals meter are the common ones you're going to see. Deci, and then we have centi. Centi is abbreviated with a C followed by another unit. And then milli is an M, again, followed by another unit. So again, remember prefixes has to be paired up with a base unit. The way this is going to work is we're going to find kilogram and then count how many times I have to move to get down to gram. And that's how many times you'll move the decimal. So here I see a K, that's kilo. So if you put your finger on kilo, that's right here. And then gram is a base unit because it's by itself, that's right here. So I have to count. It takes me 1, 2, 3 times to get down there. So my decimal needs to move 1, 2, 3. So for 0.15 kilograms, there's 150 grams. Same thing over here, 92.4 centimeters. So centa is right here. Milli is to the right, so it takes me 1 move to the right. So notice that my decimal is going to move 1 to the right to give me 924 millimeters. The last one is centi. So here we have centi, and I want to get up to kilo. So to go from centi up to kilo, I have to move to the left 1, 2, 3, 4, 5 times. So if I start here to the left, 1, 2, 3, 4, 5 times 0.45500. So both of these are examples of converting between units. So for example, the time it takes for a computer hard drive to read or write data in the range of the thousandths of second, such as 0.009 seconds, we can actually use the prefix milli to indicate 9 milliseconds is the same as 0.009 seconds. So again, 9 milliseconds equals 0.009 seconds. Another way we can use prefixes is for things that are larger. The distance is 12,000 meters can be rewritten as 12 kilometers or km. Metric prefixes turn up in non-metric units as well, especially if you've worked with computers or gaming systems. You probably know the term gigabyte for data. If you have if you have 1 billion bytes, or you could say a megapixel is 1 million pixels. And this brings into our last thing that we have to talk about, which is limits of measurements. How does the precision of a measurement affect the precision of scientific calculations? Well, first let's define precision. Precision is the gauge of how exact a measurement is, and usually we use something called significant figures to determine this. And so sig figs are digits that are known on a measurement, plus the last one that you have to estimate. So usually if you're reading something on a ruler and you have your tick marks, say if something falls between two tick marks, that's your estimated digit. One thing to note is the precision on your answer is limited by your least precise measurement. So a good example of this is when we are looking at this density problem. If the least precise measurement in a calculation has 3 sig figs, then your answer can only have 3 sig figs. So if I said calculate the density, remember density equals mass divided by volume. So if I have 34.73 grams for my mass divided by my 4.42 centimeters cubed for my volume, this one has 4 digits, this one has 3. So even though I get this long number, my answer is only allowed to have 3 digits. So we can say 7.86 grams per cubic centimeter. Accuracy, on the other hand, is the closeness of a measurement to the actual value of what you're trying to measure. A good example of this is suppose a digital clock is running 15 minutes slow. Although it's going to be precise every day and it runs to the nearest second, the time displayed is not accurate. I'm going to kind of round that up with my own example. You know if something is precise if it reads to furthest decimal. So for example, 0.004 versus 0.4. This is going to be more precise because it can read to more decimal places. If I say accuracy, this is when you're going to say, was it correct? Even if something reads to 0.004, was it an actual correct measurement? And the biggest example we can give is a clock. If you have a clock that reads to the seconds, you're going to be precise. If you have the clock that only reads to the minutes, you're not going to be as precise. And that's the end of today's lesson. If you have any questions, please make sure you ask, and I hope you guys have a great day.